over and over and going, oh, once again, this guy's just asking me for all of this context. Why couldn't they have just saved that, right? If they saved all of that information, this is now a data problem. So let's take a look at the wider Microsoft data estate. And at a high level, what Microsoft's goal is to give you a toolbox so that we can empower you to build all sorts of new wonderful experiences. And this is in contrast to other database vendors. Other database vendors will actually build a single product, hand you it, and to make an analogy, they'll tell you it's a hammer. It's a hammer. Everything out there is a nail. Don't worry about it. But the thing is that in reality, that's not how the world works, right? And in reality, what a problem might present itself in this explanatory analogy might be that that problem is a screwdriver, or rather a screw, and what you want to pick up is a screwdriver. You don't want to actually pick up a hammer, because after all, hammering in screws is just weird and ineffective. So for the broad Microsoft data estate, basically we can actually break this up into two camps. One is our on-prem data estate, and the other is our cloud data estate. On-prem, I mean, we have a battle-tested, tried-and-true product called SQL Server. You've probably used this before. I mean, it's been around for decades. It really is battle-tested. It's the industry-leading database, according to many analysts, multiple years in a row, and it's crushing it out there in terms of TPC benchmarks and other performance benchmarks. But as your application grows, you have a scale problem. You have a latency and performance problem. You want to bring that data closer to your users, and you also want to scale out. And in order to do so, basically building up data centers all around the globe is a very, very costly exercise. So to help accelerate this, what we have is, well, Microsoft Azure. And on Microsoft Azure, we can actually build some new novel database technologies to expand not just using SQL Server and shifting that to SQL DB, but actually building out a set of scale-out cloud-borne technologies like SQL Data Warehouse for your for doing deep analytics, to Azure Cosmos DB for anything that is mission critical or needs to be highly performant. When I talk about performance, I'm talking about highly concurrent workloads and delivering very, very low latency, like millisecond latency experiences. And of course, we have Azure Data Lake, where we give you scale-out storage without all the premium cost needed for a full-blown database. This gives you global reach, and we also offer this as a fully managed service, meaning that we're actually able to put financial guarantees on things like availability, on uptime, on additional things like consistency, latency, and throughput for services like Cosmos DB. And the nice thing about as you bring things up into the cloud, this also allows us to do things like build AI deep within each of our services. So for example, with Azure SQL DB, we have a index advisor. And this is where we can use intelligence to actually understand as requests come in, hey, over here, these set of queries are maybe not performing as performant as we would like. And so what we can do is we can both recommend as well as automatically, let's say, build a set of indices. Or we can do, real-time alerting. Like if we detect anomalies in your traffic pattern where this might indicate a security incident, we are on top of it. On top of this, I mean, security is a core of our business. At the end of the day, we are asking you to really trust us by moving your workload into our cloud. And so this is why we actually hire a whole army of world-class security engineers, and why we invest so much time and energy in security. This is the most secure cloud for any workload, and it's also the most compliant cloud out of any cloud vendor. On top of this, we can leverage huge economies of scale. Because we are building not data centers just for a single workload, but for hundreds of thousands of workloads, what we can do is we can leverage our economies of scale in terms of building out the real estate, all of the supporting infrastructure, the hardware itself, all the way down to personnel for managing all of this infrastructure. And so we deliver the lowest TCO out of that you can get even across other cloud vendors. And on top of this, not only are the cost of services cheaper, we can actually build cloud-borne technologies like Cosmos DB to actually exploit this fact with new novel ways of doing resource governance and further driving down TCO with upping hardware utilization. as well as the fact that this is a fully managed experience means that you spend less time, babysitting servers, patching OSs, patching software, and more time actually building things that are highly impactful and valuable to your business. We also give you the ability to easily lift and shift existing applications and modernize your application and bring them onto the cloud. And we do this through a variety of different services because at the end of the day, what we care about at Azure is choice. So whether you're using SQL Server on-premise or you're using an open source relational database like MySQL or Postgres, or using open source distributed databases like MongoDB, Cassandra, or a graph database that uses Gremlin, we actually have a powerful set of fully managed experience and services on our Azure platform. You can actually migrate them easily with little to no code changes. Beyond just databases, we actually offer you the full gambit, right? We have services around information management for actually being able to do things like cataloging or ETLing your data across different data products. We give you a lot of intelligence and machine learning products so that you can easily build models, do advanced analytics, as well as you can build dashboards and help visualize and make sense out of all of this data. Because at the end of the day, we don't just store data for the sake of storing data. What we want to do is actually drive actionable insights and get meaningful information out of this data. So with that said, let's jump into a demo. And this is the fun part, right? So what I have here is an application. It's a demo application, but it's modeled after an actual real customer use case. We have a customer using Azure named GeoSafe, and what they're doing is they're building a platform for facilitating real-time data sharing across different emergency services organizations. And so here what we've done is we've built a similar application. I'm going to log into it. And before I even log into it, I want to actually mention a few very cool things. First of all, right now, this is a geographically aware application, and it's detected that, here I am in Seattle. And what you can see here is that this application is actually available in a number of different geographic regions. And this is made possible by the fact that Azure has, 30 to 40 regions already deployed, and this is growing every day. Now, let's log into our application. And in this scenario, we have a attending police officer, John Clarkson. The first thing John Clarkson does in his day as he's cruising around in his vehicle is he's going to actually want to be aware in real time who are all of the other emergency responders that are currently patrolling and helping respond. And what we can see here is, in real time, who are all of the other fire, ambulance, and police servicemen that are patrolling around, and we can see in real time here as they navigate around, east side of Seattle. On top of this, he can also see in real time all of the incidents that are occurring around him. And as we look at some of the incidents that are occurring, here we have an incident where we have a driver who is speeding, and he wants to go and navigate over there, and he's going to go and check things out. So as he's driving over, other incidents might happen, and some of the cool technologies while he's driving over, let's actually take a look at what we're seeing here on the left pane. On this left pane, notice how the phone number is actually X'd out as well as the responding party. And this is made possible by the fact of we have a really powerful set of security and privacy-driven features in our SQL Server, including data masking. So based off of the user's privileges, whether they have a privilege to see a set of data or not see a set of data, you can actually mask individual columns. On top of this, as we're navigating to the website, navigating to this incident, what you've noticed here is that we've had another incident happen. Basically, that speeding vehicle has collided with another driver, and right away you've seen that Medic 8 has now also arrived on the scene. Now, once you get on scene, you want to actually figure out what is going on. And unfortunately, the driver is hurt, so he's non-responsive, and you're finding a hard time identifying him. However, you have overheard previously on the dispatch, someone actually recognized the driver and mentioned the driver's name is Joe. So let's type in Joe. But here's the problem. How is Joe actually spelled? Is it actually J-O-E? Am I okay to make this assumption? Well, let's actually search, because what it turns out is the person that was in the accident, looking at the picture, we've made a positive ID, is Joe Casquero. And the thing is, this is actually what's really, really cool about some of our intelligence services. Specifically, what's powering this experience is Azure Search. And what Azure Search has is this capability of doing phonetic search. So even if you don't know how to spell a name, what we can do is actually understand the meaning behind words, or do phonetic search and find similar words based off of these phonetics. So for example, if I now needed to search for John, is John spelled J-O-N or J-O-H-N? And so here what we're going to do is we've made a positive ID. We're going to select him. And what we're going to do is we're going to add a new EPCR, electronic patient care report. And on this report, we're going to list a bunch of things like the medications, other stats about the about our involved person. But on top of this, this is actually where things like Cosmos DB really, really shine. So we're going to store all of these EPCRs in Cosmos DB. And the reason why we're able to do that, why we're going to do that, is what we want to do is we want to leverage the dynamic nature of Cosmos DB and the ability to automatically index every property of every record without having to do any defining of schema up front or defining index up front. No like alter tables, no create index. And the reason why we want to do this is we actually might want to add a bunch of other metadata to this EPCR. So for example, we might actually want to tag this where we actually have some friends on site who can actually give us more detail. And I'm going to just put in Andrew as a friend, and I can actually add even additional fields. Once again, notice how I'm just adding fields on the fly without having to go back and call my DBA and tell me, hey, please go alter this table. We can actually embed this in the record and automatically index it. So we're going to also put in, let's see, something else that's missing might be the phone number. Just another piece of contact info, and we hit submit. Okay, cool. So given this application, how did we actually build this application? And here what I have is my actual application running in a VM on Azure. And basically how I've broken up my data is I have all of my incidents powered by Azure SQL DB. And the reason why I did that was just like what I said earlier, I had started building my application on-premise using SQL Server, and what I wanted to do was modernize it and bring it to the cloud so that as I expand out my first responder application business, I don't want to just actually build this for the Seattle PD. I actually want to expand this out and make this available to all emergency responders nationwide. And to easily do so, I've brought this up into the cloud. I've moved this onto Azure SQL DB. And on top of this, I have now also taken advantage of the Elastic Pools feature in SQL DB to elastically scale this workload out. And so let's take a look at the code base here. I'm actually having this run live. I've set a breakpoint on whenever a request comes into the system, so we can also get an idea of what is the behavior. But basically what this is doing is a fairly simple query. I'm basically just asking the database, grab me all of the incidents with a variety of different filters that I will add depending on whether it's a fire incident, a police incident, or so forth. So let's fire off a request here. I have here a PowerShell script for also setting up my shard map manager for Elastic Pools. So actually, let's step through this and see what's going on. The first thing I'm going to do is I'm going to pull in this shard management module, and I'm going to configure it to connect to my SQL database. And once I get that module set up, I can now invoke my API. One thing I do want to point out is this is actually all live happening in front of you. We actually have all of this code deployed on GitHub if you want to play around. And the way we've set up our Elastic Pool is we have 3 database shards, one for the ambulances, one for fire, one for police. Now, I have a REST API set up for my application service, and if I call this /API/incidents, then I basically will get a dump of all of the incidents. So here I'm going to actually hit the breakpoint for my application. And right away, what you can see is I'm going to pull in the same config for all of my database shards. I'm going to get actually my shard map. You can see that I have the same 3 database shards. And then what I'm going to do is I'm going to use that library that allows me to now fan out this query or route my incident query across all of my different shards. Once I call that library, what you'll see here is I get a dump from my database, all of the incidents that's happened in real time. On top of this experience, we're not just looking at incidents, but we actually wanted to leverage the fact that we have all these other Azure technologies, and what I want to do is provide that search experience that you saw, as well as that ePCR experience. So here, what I'm going to do is I'm going to go and jump into, let's see, actually, before I even do so, let me actually show you another cool thing about Elastic Pools. So you saw that I have right now a set of databases put on a pool, and let's take a look at how easy it is to actually scale my application. So let's say tomorrow that it's not just the Seattle PD that is interested in the application, but I'm now onboarding the Atlanta Police Department, maybe the Oregon Police Department, and so forth. All of these different first responders all around the country. And so what I'm going to do is I'm going to click on my DTU. I'm going to configure the pool. And here you can see how easy it is to actually scale my database. So as soon as this load, what you're going to see here is an idea of what is the actual DTU and storage usage. And the concept of a DTU is it's basically a logical abstraction over all of the physical resources it takes to fulfill a request. The CPU, the memory, the network I/O, the disk I/O. And the reason why we do this is it makes scaling a lot easier. Because at the end of the day, if I need to grow this application and I'm wondering, you know, do I buy more memory? Do I buy more CPU? It's actually really hard to say, right? For today, you might stress the system. You might actually find that the immediate bottleneck is memory, but then you're left wondering how many gigabytes of RAM translates to how many requests, right? By simplifying this model to just a single logical abstraction on top that's specific to this workload, we're actually able to give you a single dimension to easily scale this workload. So now I see that today I have low usage, but I have a new customer getting onboarded. So if I want to scale, I can easily just drag a slider and hit save, and that'll scale my Elastic Pool. Now let's take a look at those ePCR entries. These are being powered by Azure Cosmos DB because now that my application has been migrated to the cloud, I can actually leverage a lot of these really cool cloud technologies. One of which, for Cosmos DB, is going to be the ability to automatically index properties on the fly, add new properties, index those, and query them efficiently. To give you an idea of what these records look like, here we have both our tickets and our ePCRs in 2 collections, a tickets collection and a patient collection. And what you can see here is I'm just doing a simple query. I'm using the SQL Query API. I'm going to just do a select star from this collection. And what you'll see here is I have a set of records for each of the tickets I have in the system. Now, important things to note about these tickets. Number one is this field, location. If you have played with GeoJSON before, it's basically a standard for representing latitude, longitude coordinates. Another really interesting thing about Cosmos DB is it supports geospatial query. So not only is it a distributed database, but as you build a distributed database, you don't actually have to sacrifice queryability. On top of this, you can also see that I have a set of fields. They're nested within an object, and this is because Cosmos DB allows you to do nested objects, nested arrays, storing very, very complex object types. This allows you to denormalize your data. It also allows you to add properties, remove properties on the fly, because each of these records is actually going to describe exactly what properties it has, what type it is, and what is the value. On top of these GeoJSON points, what I can do is I can run geospatial queries. And so here I have a geospatial query. You saw in that application I've basically added a bunch of tickets and a bunch of ePCRs to the system. And you know what, as a supervisor of the system, I actually might want to go back and take a look at, you know what, let's actually take a look at all of the traffic tickets that have happened within a certain neighborhood, just to get an idea of, you know, what is the level of risk? Like, am I seeing a lot of incidents in this neighborhood? Do I actually need to staff this higher and increase the amount of patrols here? On top of this, another really cool thing that we can bring to the table as a cloud platform is the fact that Azure is available in 30 to 40 geographic regions already. And what we can do here is we can actually use this to actually build a globally distributed database. And that's exactly what Cosmos DB is. Today, we might have deployed the application in a single region. It's in West US because, you know what, I'm currently in Seattle. However, like I mentioned, we might have a few emergency responders who are interested in onboarding onto this service. And what we'll want to do is actually bring that data closer to our users. So at the click of a button, I can actually replicate my data to any number of regions of my choice. And I do this by just clicking what data center I want to add, and I just click on save. And by doing so, what I'm doing here is basically exploiting properties around data locality. And if you're building a real-time application like this first responders application, the thing is that latency is very, very critical, right? If you are late to the game on showing up for an incident, you know, things might not actually work out very well. So what I want to do is I want to deliver a very low latency experience. However, this actually brings a fundamental problem. If I have a single database endpoint, I now have to send packets no matter where the user is. Let's say it's the Atlanta Police Department all the way to where the database is hosted. If that database is hosted across the continent from me, even under ideal network conditions, packets can't travel faster than the speed of light. So you're looking at round-trip latencies of around like 70, 80 milliseconds. This problem gets even worse if you have users on a global scale, because as you ship packets on a global scale, you're looking at several hundred millisecond latency. The way you actually cheat the speed of light is you don't actually send a packet faster than it. I mean, if I figured out how to do that, I guess I'd win the Nobel Prize and probably wouldn't work here. But the way I cheat that is I bring the data very, very close to my users, right? So if a user happens to be in Atlanta, then he should be talking to a data center closest to him. Meanwhile, a user in Seattle should be talking to a different data center, whichever data center that he is closest to. And so by the fact that I'm replicating this data to all these different geographic regions, I have a tunable consistency model to actually get predictability and the behavior on how things get replicated and read. And I can do so with very, very low latency. It means that the application experience for my user is very robust and fast. Now, this is only one view of the application where I am connected as John Clarkson. Let's take another view of this application. So I'm going to reopen it, and I'm going to log in as its supervisor, Eric Dodds. And so as a supervisor, Eric is not actually going around and patrolling himself, but what he wants to do is actually monitor and understand where are all of his first responders, what are all of the incidents happening, but not just reactively handling each of these incidents. He actually wants to get ahead of the curve. He actually wants to now dispatch and tell any kind of idle first responder where he needs to be able to react quickly. And so this is where we're going to build intelligence into the application. And what he's going to do here is he's actually going to, in real time, build a heat map so he can understand where are the areas right now that are vulnerable to incidents. Like, what is the probability of having an incident? And what he's going to do is he's going to build this, this heat map overlay. Let's take a look at how this heat map overlay is built. So basically, what we're going to do is we're going to build a machine learning model. And what we're going to do is we're going to use R. So the first thing we're going to do is, because we have all of the incident data available to us, what we're going to do is we're going to leverage the new intelligent capabilities in SQL Server, in which we can embed R or Python logic and use this to actually build intelligent models that we can then query in real time. But first, let's actually build this model. And the way we're going to do that is first we're going to get all of the incidents out of our data set. So here what I've done is I've run a query and I've pulled out all of the incidents out of my database. I'm going to clean this data set. And now I'm going to actually pull out a few columns that are actually relevant for building out my model. Once I've done that, I'm going to normalize it. I'm going to split it out. And now that we have all of our data sanitized, we're ready to train our model. So here we're going to just do a random decision forest on top of this data so that we can actually calculate the probability or the number of incidents that are likely to happen given a set of parameters. So here I'm going to run this line here to build my random decision forest. And what you'll see here is I'm building this model right in front of you. Once I have my model built, I can actually plot it out. And this will give me an easy way of actually visualizing what does the model look like and using this as a way of calculating how many incidents I can expect. Now, here's the cool capability that we've just introduced with the new version of SQL Server. Basically, what I can do is I can build a model, or actually rather, I can store the model in SQL Server. I'll give you an idea of what this looks like. Whoops. One sec. Here you can see I've actually materialized my model. And what I'm going to do here is I'll show you actually how I can leverage this. And so what we can do now is we can, because we are hosting both R and Python runtimes within SQL Server, what we can do is we can actually copy paste our R code into a store procedure. And so this is the exact same code that I just showed you. And because I've already created this stored procedure, what I can do is I can now execute a stored procedure that I use to predict the number of incidents. And within it, I'm going to feed it a number of parameters, like the current temperature, the wind speed, how much rain I'm observing. And if I hit execute, given these set of parameters, what you'll see here is we'll be leveraging that model, and what you'll see in the query result is a number of incidents predicted given these set of parameters. Oops, let me try this again. So these are the things that can happen in a live demo, but I'll basically tell you what's supposed to happen. Basically, in the result, you're going to see a value. It's going to be something. My guess here, using my human machine learning model in my brain, I expect an output of around like 1.3 to 1.9 incidents. We'll try this again after the query gets canceled. So on top of this, this actually isn't the only things you can do with our vast data estates. But on top of this, we actually have tools for visualizing the data with Power BI. So Eric Dodds, as a supervisor, he actually wants to get a lot of business insight, or rather analytics and insight into the incidents that are happening. And so here he's going to use Power BI embedded, and off of the exact same data set, he set up a number of dashboards. You can actually then segment the data in a variety of different ways, let's say only looking at person crime or property crime. And with that, he can actually see how fast are we able to respond, how many incidents are we seeing, how many of them are high priority, as well as kind of the incident volume over time. Not just segmenting by type, but we can also segment this data set by the responding officer. So this way we can also get an idea of how our officers are doing, what kind of incidents they're responding to, as well as what are they seeing. So are they seeing a lot of incidents related to, let's say, an intoxicated driver, or if they're seeing something else. Actually, if we select different officer, looks like we have a lot of DUIs in this data set. On top of this, you can build very, very rich experiences. You can customize a dashboard and make this very interactive and answer a lot of business questions or other sort of questions that are helpful for your specific scenario. And this way, you're not always having to deal with, let's say, a very static-looking report that you might get, let's say, on a daily job or a weekly job in email, just a PDF document. Instead, you can actually interact with this in real time and actually understand not only if an anomaly occurred, why that occurred. So let's take a look at the architecture for this first response application. As I mentioned, all of the incidents are right now getting powered by Azure SQL. We're using the new R functionality to build a machine learning model and also predict what is the probability as well as the number of incidents I can expect. I'm using the Elastic Pools feature to actually scale up my existing Azure SQL DB workload. I'm also leveraging new cloud-born technologies like Azure Cosmos DB to also then bring this data closer to my users to deliver very, very low latency experiences, as well as build a schema-agnostic way of then, as I annotate my ePCRs or my tickets with new properties, new kinds of information, being able to then automatically index those without having to do any kind of database migration script, no alter tables, no create index. Instead, it's just indexed. It's consumed, and then I can easily query over this very, very efficiently. On top of this, I had the experience where I showed you phonetic search, where I typed in Joe, and what you found is that Joe, in this case, the person I was looking for was spelled J-O-A-O as opposed to J-O-E. What I've done is I've used the out-of-box search integration with Cosmos DB, where I'll take all of these incidents data, all of these tickets data, all of these different ePCRs. I can actually take a look at the name property, build a full-text search index on it, and then apply a different set of analyzers, whether I want to use a NLP-based analyzer for understanding the meaning of words, if I want to do search like mouse versus mice, or I want to do phonetic search like Joe versus, well, Joe. This is powered by Azure Search, and then on top of this, we can actually leverage a whole other suite of cognitive services so that if I want to do, let's say, speech recognition and then query my database using speech because I'm driving in a vehicle, I can actually do that text-to-speech and then query over my search index on Azure Search in real time. I'm also leveraging Azure Functions here for each of these different databases, and so that way I can actually build a true serverless experience and build a way for growing my application while keeping it very, very manageable and easy to scale. So with that said, if you'd like to try out the application yourself, deploy it, play around with it, we actually have it open sourced on GitHub. And for today's agenda, what we wanted to do was cover basically an overview of the wider Microsoft data estate, as well as give you a demo of what are some of the really cool things that you can actually build off of this. We'll have another follow-up session tomorrow at 3 p.m. It's called Building Planet-Scale Apps with Real-Time Personalization. But what we'll do is we'll actually do a much more technical deep dive within that. We're going to take one of our Azure services, specifically Cosmos DB, and we're going to actually do a technical deep dive of how you actually want to approach design, from partitioning to replication to tuning consistency. With that said, I'd like to open up the floor. You are able to ask questions here, and I am happy to answer. Looks like my question feed is not working properly, but that's okay. You can always feel free to reach out to us. We're super active on Stack Overflow, on social media, on things like Twitter. Do feel free to ping us. We're always actively monitoring these different channels. We're more than happy to answer. And do check out our session tomorrow. Thank you very much.